Okay, so today we're working on section 15.1. So this is part of chapter 15, which is about sound. So, main idea, perception of a sound wave depends on that wave's physical properties. And so 15.1 is going to be pages 973, 976. Not very long, but it actually has quite a bit of stuff. First of all, sound waves. We realize that sound waves are longitudinal waves and that they have to be gone through some sort of medium to be able to get them to go from one spot to another. Now, sound itself, as we said, is a longitudinal wave, and you can see that in figure 1 on the right-hand side. And as we take a look at that figure, you'll notice that in places of high pressure and low pressure, those are generated by the clangor inside the bell hitting the wall of the bell and forcing it to vibrate, forcing the air particles to get closer together. That's the high pressure, and farther apart in the low pressure. So, as we see with pressure variations, as the bell moves back and forth, the edge of the bell strikes the particles in the air. And when the edge moves forward, air particles are driven forward. So what we're talking about is it goes back and forth, what we call an oscillation. So oscillations are incredibly important for this because it generates that air pressure that we pick up as sound in our ears. Now, with that, waves themselves, sound waves, basically have everything that you'd find in a regular wave. It says a pressure oscillation that is transmitted through matter is a sound wave. Sound waves travel through air because a vibrating source produces regular variations or oscillations in air pressure. Skipping down just a little bit, the frequency of the wave is the number of oscillations. Wavelength is distances between successive regions of high or low pressures, just like any other wavelength. And because the motion is parallel, it's a longitudinal wave. Two other real important things. Just like any other wave, the speed of the sound depends on the medium through which it travels. And the more together that medium is, the more rigid it is, the faster it's going to move. And also in air, the speed depends on the temperature by about 0.6 meters per second for each 1 degree Celsius increase in air temperature. We're going to be getting into that and give you an equation, pretty simple equation to be able to figure out the speed of sound. So now with this, we also see here that in general, the speed of sound is greater in solids than it is in liquids or in gases. Once again, it's the rigidity. And also sounds can't travel in a vacuum, so there's no sound in space. You need a medium for that pressure to be going and to be transmitted along. In a vacuum, there are no particles to get crammed together or spread apart to generate that pressure for sound. You'll see on the right-hand side the speed of sound in various media. And you can use that with using the equation velocity equals distance over time to figure out how fast it is on the right-hand side, but you can figure out then the distance or the time it takes for it to go through that particular material. And once again, the more rigid, faster it goes because the particles are together, and so they affect each other more. If they're spread out, not so much. So pretty quick, should be able to get through that pretty quickly. That's the launch for 15.